your homework is bring them up here. Get started. Are there any questions about anything before we get to today's material? Okay, everyone's following so far with the material and parameter inference, model inference. Okay, well, I guess we'll move on to the material for today. And what we'll be talking about today is a kind of specialized version of model inference that comes up in a lot of different contexts in biological modeling, known as interpolation and extrapolation. And I can illustrate what these things are by talking about a few examples of where they come up in practice. So, one instance where we might be interested in applying this particular kind of modeling might be that we're working with a model that's meant to integrate with some kind of experimental data. So maybe we've got a model of a genetic regulatory network. Some component of this model is represented in terms of a set of differential equations. We've got some, say, dx dt equals ax. But we assume that this is being driven by some outside stimulus. So maybe we've got a model of how a cell responds to external hormonal signals, and we want to see how that model would respond to some kind of aberrant signaling. So we might assume that this has some driver term, an external signal that's a function of time. We want to plug that into our model. Now, if we're trying to do this with actual experimental data, there's a problem here, which is that this is a continuous model, but experimental data is very often going to be discrete data points. So it might be that we have a set of points in time at which we've measured the value of this signal on an actual system, and we want to plug these points in time into our continuous model. And to do that, we need some way of taking our discrete set of points and turning them into a continuous model that we can measure at any value in time, even if it's between the data points we actually measured. So in a case like this, what we would very often want to be able to do is to fit some curve to these data points as something that we can then feed into our continuous model and pretend that we have a continuous model of the real experimental data. So that's one example of what we would call an interpolation problem, trying to be able to figure out what that experimental curve should look like at all the data points we didn't measure between the ones we did measure. So any questions about that? All right, another instance where this kind of thing comes up is that sometimes we're interested in long-term trends in a system, so maybe longer term than we can actually study practically. So maybe we've got a simulation model, and it's generating some process. You might get a set of data points, maybe something like this. And what we're interested in is what this does in very long amounts of time, but it might be that this is a computationally costly simulation. We can't run it for an infinite amount of time. We'd like to know what this does if we were to run it for an infinite amount of time. So that's another case where often we're trying to do a kind of projection to figure out where this thing is headed over very long time scales. And that would be an example of an extrapolation problem, taking a finite set of data points and trying to extrapolate to a limit of what those data points seem to be doing. Another example we would often encounter is that very often we're working with real data. That real data is going to be noisy. So it might be that we've got a set of data points, and we know that these data points maybe are approximating some physical process, but there's a significant amount of noise to them. So maybe there are some large outliers, some random noise within the data points. this is a case where very often what we would want to be able to do is to try to smooth the data a bit. Say that maybe there is some curve that's actually a better measure of what the real process is doing than the actual data we've got on that process. Very often, if you've got a lot of data points, this kind of data smoothing approach will actually give you a better inference of the real physical system than the raw data coming off of some kind of measurement machine. So that's another case where we might be interested in using an interpolation method to try to fit some smooth model curve to the data available to us. Similar things come up when we might be interested in testing some hypothetical models for a set of data. So maybe we've got some discrete data points, and we want to consider, are these data points consistent with a linear model? Are they consistent with an exponential model? Are they consistent with maybe a sinusoidal model? And come up with some way of figuring out for these different kinds of models which are most or least consistent with the data. And there again, we might be interested in fitting some kind of curve to the points we have. In other cases, we might be interested in generating a continuous model with an inherently discrete simulation method. So maybe we're trying to study movement of a particle under Brownian motion, and we decide that we're going to do a lattice model of that. So we'll create a Markov model where a particle is shifting between different positions in the lattice as a function of time. And we want to be able to take these discrete jumps and fit a finer scale model of what this particle might be doing on top of them. So to maybe say that there's probably some smoother curve that the particle is passing through. And there again, we're trying to solve the problem of taking some discrete data points and coming up with a continuous extension of them, at least mapping to a final resolution we've actually simulated. One final application that comes up quite a bit in image analysis related contexts is that very often we've got some discrete set of data and we want to change the resolution of that data. So maybe we've got a library of images and we're trying to do some comparison of them, and some of the images are at different resolutions than other images. So what we might want to do then is come up with a way of picking some common resolution where we can compare these and figuring out for that common resolution of interest to us, what would this image and this image look like on that common level of resolution. So that's another case we might be interested in asking for some set of points that maybe don't line up nicely with the pixels in our actual image. What should the values be at those points? And these are all examples of interpolation and extrapolation problems. So that's basically the kind of problem we'll be talking about today. So are there any questions about what we're looking at or motivation for any of these things? Okay, well, if not, I guess I'll start with probably the simplest way of doing this. And probably the most widely used and simple way of doing these kinds of interpolation and extrapolation problems is to use polynomial fits. So basically take our data points, try to find a polynomial that provides a good description of the data we observe, and then use that to do your interpolation. So ask what the value of the polynomial is at any data points you don't get to observe. So in a theoretical sense, what we can say is that we have some input, let's say x1, y1, x2, y2, up through xn, yn. And in the simplest version, what we would want to say is that there is some unique polynomial that passes through all of these points perfectly. And in that case, we can say, as long as we've got a non-degenerate set of points, it's going to have to be an n-1 degree polynomial. And then we can just ask, what is the unique n-1 degree polynomial that passes through all of these points? All right, so let's start with that problem. We've got this set of data points. There's actually a relatively simple kind of procedure to generate an equation for the polynomial passing through all of these points. And I'll just write what this looks like. So basically what we would say is that we have a polynomial, it's a function of x, we want it to match all of the y values, and we'll do that by creating one term for each of these data points. It's going to look as follows. So we'll have a term for this data point, and it's going to look like x minus x2 times x minus x3 times x minus x4, etc., up through x minus xn. So a term of this form, x minus xi for everything except x1. We divide that by the same thing, except plugging in x1 for x. So x1 minus x2, x1 minus x3, etc., multiplied up through x1 minus xn, and then multiply that whole thing by y1. And then we'll do another analogous term for the second data point and the third, and so forth. So for the second one, the numerator would be x minus xi for every xi except 2. So x minus x1, x minus x3, x minus x4, etc., for x minus xn, divided by now x2 minus x1, x2 minus x3, etc., up for x2 minus xn times y2, and then just repeat that for each of the data points. And I'll assert that this is a formula that actually gives you a polynomial of degree n minus 1 that passes through all of the data points. So is it clear what the pattern is here? Right, so it's actually not too hard to verify that this polynomial has the properties we want it to have. And to see why that's the case, we can plug in, let's say, x1 into each of these terms and see what happens. So if we plug in x1 here, what we're going to get is the numerator is x1 minus x2, x1 minus x3, etc., up through x1 minus xn, which is exactly the same thing as we have in the denominator. So this whole thing goes to 1, and this term becomes y1. What happens if we plug in x1 for x in this term?
It goes to 0.
Yeah, because we've got an x minus x1 term, so that becomes 0. And all of the other terms will also have an x minus x1 term, so they all go to 0, and the final value is y1, which is what we wanted. So the same thing would work if we plug in x2, x3, or whatever. So this gives us kind of a simple procedure for generating the polynomial we want. It is kind of a messy, cumbersome procedure, and it doesn't obviously generalize to anything other than getting this one particular polynomial, though. So there are better ways to do this, and I'll go through one of those in a moment. Are there any questions about this before I get to a different way of getting these polynomials?
So this one seems like it overfits.
Yeah, that's part of the problem. So if you get a polynomial that's actually matching every point, it's very likely to overfit. So we'll see a bit later how we would get a polynomial that's maybe lower than degree n minus 1, which is actually usually what you would really want to do. Any other questions about this? Right, so often if we wanted this polynomial, what we would really want to do is use a different technique called Nepals Algorithm. And Nepals Algorithm is a way of generating the same polynomial, but it does it hierarchically by building up from successively simpler polynomials. And the basic idea behind it is that we're going to create a family of degree 0 polynomials such that each point is matched by one member of this family. So we've got one degree 0 polynomial that gets the first point right, another gets the second point right, and so forth. And then we'll merge degree 0 polynomials to get degree 1 polynomials that match pairs of adjacent points, then merge those to get degree 2 polynomials that match triplets of points, and so forth. So that can give you a way of getting simpler approximations to subsets of the points and eventually getting to the complete polynomial here. And the way that works is as follows. We're going to start by taking our 0th order polynomials. So I'll call those P11 of x will be the 0th order polynomial that matches just the first point, P22 of x matches the second point, P33 of x matches the third point, and so forth. And then we're going to take pairs of these to get a first order family of polynomials. So we'll have the polynomial P12 of x, which we'll assert matches points 1 and 2. We'll combine them to get a P23 of x, which matches points 2 and 3, and so forth. And then we'll merge these to get second order quadratic polynomials. So P13 that matches points 1, 2, and 3, and so forth. And we can do this with a relatively simple formula for taking the approximation at any given order and finding the next higher accuracy approximation. And it works as follows. We'll define Pi, comma, I plus m. So the polynomial that matches points I through I plus m to be the following. X minus x I plus m times P I plus m minus 1 plus xi minus x P I plus 1 comma I plus m. And then that whole thing divided by xi minus x I plus m. So in other words, what this is saying is that we're going to construct a polynomial of order m by taking two polynomials of order m minus 1. Everyone follow that? All right, so let's see why that would actually do the right thing. Right, so let's imagine that we are looking at an interval. So we've got one polynomial that matches from I through I plus m minus 1. We've got another polynomial that matches I plus 1 through I plus m. And what we're going to try to do is prove inductively that this formula is going to give us a polynomial that matches over the entire interval, that gets all of the points right between I and I plus m. So the first thing we'll do is ask, what happens if we plug in an xj that's in this interval from I plus 1 to I plus m minus 1? So in other words, a point that both of these polynomials by our inductive assumption already get correct. Well, if we do that, what we're going to end up with is plugging xj in for x in the formula. We'll get xj minus xi plus m, pi I plus m minus 1 of xj, plus xi minus xj, pi plus 1 I plus m of xj, over xi minus xi plus m. All right, so what is p of I plus m minus 1 of xj? Well, by our inductive assumption, this is the value of a point in the region covered by this polynomial. So this polynomial has to get the right value from our initial set of points. That's our inductive hypothesis. So this thing is going to be yj. What is this thing, pi plus 1 I plus m of xj? Well, that's also in the region covered by the right polynomial. So that's also going to be yj, because again, our inductive hypothesis is that both of these polynomials get the points right in that region. So that's yj. And then we can start canceling some things out here. We've got a plus xj here, a minus xj here. These are both yj. So if we put this all together, what we're going to get is these cancel out. We get an xi minus x plus m times yj over xi minus xi plus m, which equals yj. So in other words, this is going to give us the right answer for this particular value of x. So basically, if we're in that interval that's covered by both of the original polynomials, this will do the right thing. Does that make sense to everyone? All right, so what happens then if we plug in a point that's only covered by the left polynomial? So we have one point xi that the left polynomial gets right, but that we're assuming the right polynomial may not get right. Well, if we plug that in, what we're going to end up with is xi minus xi plus m, p of I, I plus m minus 1 of xi, plus xi minus xi by xi of I plus m minus 1 of xi?
That should be accurate.
What's that?
Was that the one that was it the one outside?
Yeah, so that's the point here that's covered by the left polynomial.
Like your y, j,
Yeah, so in this case, yi. So by the inductive hypothesis, again, this polynomial gets that point right. This other polynomial may not get that point right, but it doesn't matter because this is 0, so that goes away. These two things are equal, so we end up with yi. So it'll do the right thing if we pick the point on the left endpoint that's only covered by the left polynomial. And the same thing more or less happens if we pick the point on the right. We get xi plus 1, or excuse me, xi plus m minus xi plus m, pi I plus m minus 1 of xi plus m, plus xi minus xi plus m, p I plus 1, I plus m of xi plus m, divided by xi minus xi plus m. And in this case, this thing is 0 here, so that goes away. It doesn't matter what this is. By the inductive hypothesis, this is yi plus m. These two things are then equal, so they cancel out. And in the end, we get yi plus m. So what that's basically showing is that the induction works, that if these two polynomials get the intervals they're covering correct, then putting them together by this formula is going to give us a polynomial that gets points covered by both regions correct. So it's going to expand the interval by a size of 1. So it's not quite a complete inductive proof yet. What's missing?
base case?
Yeah, so we're going to need a base case for this to work. And our base case is going to have to be something that we can give us that will give us 0-order polynomials such that at each point we've got a 0-order polynomial that gets that one point right. So let's start with this point. We are asserting that there's a 0th-order polynomial p11 of x that gets this point right. What would p11 of x have to be?
Y, I, or y1.
Yeah, y1. So this is just a straight line at value y1, but that means it gets it right at that point. And likewise, p22 of x is y2, and so forth. So if we put that together, then we've got our base case, and that makes a complete inductive proof that we've got an algorithm for getting successively larger polynomials that will get more and more of these points right at each step of the algorithm. Does that make sense to everyone? Okay, well, let's then look at an example to see how this would actually work in practice. Suppose we take the following set of points. So let's say 0, 3, 1, 5, 2, 2, and 3, 4. I'll just try plotting what these would look like. So we've got 0, 1, 2, 3, 1, 2, 3, 4, 5. And this is saying we've got a point here. So we've got 1, 5, we've got 2, 2, and we've got 3, 4. So these would be our points. And then we start by creating our 0th order polynomials, and we'll get p11 of x has to be identically 3, p22 of x has to be identically 5, p33 of x is identically 2, and p44 of x is identically 4. So if we were to draw that, this would be p11 of x, this would be p22, or excuse me, p33, p22, p44, and so forth. And we could then apply Nepals algorithm to try to put together some higher order polynomials that would get pairs of points right. So we could take these two, for example, and Nepals algorithm says that the formula to put together p12 of x is going to look like x minus the value of x, or the value, right endpoint, which is 1, times the value of the function at the left function, which is 3, plus the value of x at the left endpoint, which is 0, minus x, times the function at the right side, which is 5, divided by 0 minus 1. And if we put all of that together, what we're going to get is that this reduces to 2x plus 3. And you can observe that this is, in fact, a first-order polynomial. And if we try plugging in values here, what we're going to get is that the left endpoint, if we plug in x equals 0, we get out 3, which is what we want. And if we plug in x equals 1, we get out 5, which is what we want. So this, we know now, is getting both endpoints of that first interval right. We could do the same thing with the others, so we can get P23 of x, which is going to be x minus 2 times 5 plus 1 minus x times 2 over 1 minus 2, which will, with some reducing, become minus 3x plus 8. And we could verify that if you plug in 1 there, you get 5. If you plug in 2 there, you get 2. So it's matching these 2 points. And finally, P34 of x is going to be x minus 3 times 2 plus 2 minus x times 4 over 2 minus 3, which will become 2x minus 2. And then again, we can observe you plug in 2, you get back 2. If you plug in 3, you get back 4. So this is going to give the right answers. So does that make sense to everyone so far? All right, so we can then take that another step. We can take P12 and P23 and find P13 of x. We're going to get that by saying x minus the right endpoint, which is 2, so that's the right thing covered by P33, times the value of the left polynomial, which is P12, we decided was 2x plus 3, and then that's plus the left endpoint, which is 0 minus x, and the right polynomial, negative 3x plus 8, and that's going to, that's going to be divided by 0 minus 2, and this whole thing is going to reduce to minus 5 halves x squared plus 9 halves x plus 3. So it's one higher order, and we could verify if we wanted to that this will now get 0, 1, and 2 correct. And likewise, we could get P24. That one's going to be x minus 3, so x minus the right endpoint times the left polynomial, negative 3x plus 8, plus left endpoint minus x times the right polynomial, 2x minus 2 over 1 minus 3. Will come out to negative 5 halves x squared minus 21 halves x plus 13. Again, we could verify if we wanted to that this is giving us the right answers at points 1, 2, and 3. And the final step would be to combine these. Won't bother writing out all of the math, but if we apply the formula at these two equations, we should get a cubic, and indeed it will come out to 5/3 x cubed minus 15 halves x squared plus 47/6 x plus 3. And I'm not going to try plugging in all the numbers, but we can at least plug in 0 and verify it gets that one right, and then if we actually try 1, 2, or 3, you can verify that this gets all of the numbers in our interval correct. So basically that's Nepals' algorithm, and if we had many more points, we could keep going and getting higher and higher order polynomial, but probably if you've got a lot of points, you don't really want a polynomial covering all of those points. Any questions at this point? Okay, so the issue was brought up earlier that if you have too high an order polynomial, you're probably going to run into problems of overfitting. So basically what's going to happen is something like the following. If we've got lots of data points, maybe we've got a bunch of data points, look something like this, we can kind of see that there's a trend here. These data points are more or less a smooth pattern. But if you actually try to fit a polynomial to them, if there's even a little noise to the data points, what it's going to do is something crazy like this. It's going to manage to hit every point exactly, but by doing basically wild swings all over the place to manage to get all of them. When probably looking at a data set like this, we'd probably say the actual model should be something more like the following. It should be a much smoother curve that maybe doesn't hit every point exactly, but comes pretty close to it. So very often what we want to do is infer that smooth curve, and usually the way we would do this is by trying to fit a simpler model. And if you're trying to fit a polynomial model, what that means is trying to fit a lower degree polynomial than the n-1 degree you would need to actually hit every point exactly. And so what I want to do is go through briefly how we would solve that problem. And we've actually seen earlier in the term how you would solve that, so this should be somewhat reviewed, but then we'll see how to generalize some of these methods. So in particular, let's say we've got our set of points. So again, we've got x1, y1 up through xn, yn. And I'm going to assume that what we're trying to do is fit a kth order polynomial for k much less than n. So we're going to try to find a model of the form c0 plus c1x plus c2x squared, etc., up through c sub k x to the k. Now let's pretend for the moment that we could get a model of degree k that actually did hit every point exactly. So if we had this model that hit every point exactly, then what we would end up with is a set of constraints specifying how that model works. And they're going to look something like the following. We're going to have c0 plus c1x1 plus c2x1 squared, etc., up through ck x1 to the k is equal to y1. That's just an assertion that the polynomial gets the first point right. And likewise, c0 plus c1 x2 plus c2 x2 squared, etc., up through ck x2 to the k equals y2 would be an assertion that it gets point x2, y2 correct. And likewise, we would end up having n of these, so c0 plus c1 xn plus c2 xn squared, etc., up through ck xn to the k is equal to yn. So we've got a set of constraints that tell us what this function should look like if it actually fit all of our points exactly. And what you should note here is that these constraints are linear in the coefficients we're trying to learn here. And because they're linear in the coefficients, we can put these constraints in the form of a linear system. So we can say that we've got a matrix, we've got our unknowns that we're trying to learn, which are the coefficients, c0, c1, up through ck. And what we're really asserting here is that this first equation would be the first row of the matrix times this vector equals right-hand side here, y1. So in other words, we would get a c0, or excuse me, we would get a 1, an x1, x1 squared, etc., up through x1 to the k. And in the second row, we would get 1, x2, x2 squared, through x2 to the k, equals y2, etc. And we would have, in the end, n of these, so 1, xn, xn squared, etc., up through xn to the k is equal to yn. So if we had a polynomial that exactly fit all of the points, then we would be able to find the coefficients that satisfy this linear system. I've asserted, though, that we are assuming k is much less than n. So what does that tell us about this linear system? Well, if we look at the dimensions of the matrix, we've got n here, we've got k plus 1 here. This vector is length k plus 1. This vector is length n. So, what's that? What's that?
Overdetermined?
Yeah, so this would be an overdetermined system. So we've got a lot more equations than unknowns. In general, that's going to give us an overdetermined system. And so we're not going to be able to get a solution, so a set of coefficients that get all of our points exactly right. But we can come as close as possible by some measure. And how would we usually do that for an overdetermined linear system? Well, the most common thing we had seen is to try to get a least squares best fit. So if you remember, usually when we have an overdetermined system, the easiest thing to do to get as close a solution as possible is to do the least squares fit, where basically we're minimizing the sum of squared errors in these approximations. So we're minimizing the sum over each of our terms, say I equals 1 to n of the approximation c0 plus c1 xi plus c2 xi squared, etc., through ck xi to the k minus yi quantity squared. We're trying to find a solution that minimizes the sum of that over each of our equations. That's a least squares solution. And this is something that's not too hard to do with an overdetermined linear system. So if we call this matrix X, we call this vector C, we call this vector Y, then what we're going to end up with is that what we want is C is the solution to the linear system X transpose X, C equals X transpose Y. Solve that linear system, then we get the least squares optimal value of the coefficients. So does this sound familiar to everyone? Okay, any questions about this yet? Okay, it's worth noting that this isn't necessarily the only way of solving this problem. It tends to be the easiest way of finding a best fit low degree polynomial to a large number of points. But we could pose this differently if we wanted to. So least squares is equivalent to solving what's called the L2 metrics, the L2 norm of the solution. Let's say instead we wanted the L1 norm. So the L1 norm is the sum of absolute values. So if we wanted the sum, I equals 1 to n, C0 plus C1 x1, etc., up through CK xi, excuse me, Ci xi to the k minus yi, and just minimize the sum of absolute values of these. Can anyone think of how we might find that solution? That tends to be kind of a tricky one. The way we would often solve this is to create what we would call an auxiliary variable. So we could say that there is some zi, and we will define zi such that zi is greater than or equal to c0 plus c1 xi, etc., up through ck xi to the k minus yi. And we'll also define that zi is greater than or equal to minus c0 plus c1 xi, etc., up through ck xi to the k minus yi. And what this is asserting is that, in effect, zi is something that has to be at least as big as the absolute value of this, what we call a residual term here. And what we would then want to do, once we've defined these zi's, is find the thing that minimizes the sum of the zi's. And that's going to have to be the set of coefficients that minimize the sum of absolute values of our residual terms. So how could we do that?
We could minimize the squared error of zi minus that, the other quantity.
Well, that would be a slightly different way we could pose this. That would give us a slightly different measure than minimizing the sum of absolute values. But we can do this pretty precisely. What we do then is minimize the sum over I of the zi's. And what we've done at this point is we've turned this into a linear program where the variables are the zi's and the ci's. So the ci's are the coefficients we actually want to know. The zi's are things that will be forced to these absolute values. So basically what we've done is turn it into a linear program. And we should know how to solve those, so that's what you could do if you wanted to find the best L1 solution instead of the best L2 solution to this polynomial problem. That makes sense to everyone? All right, so if we had more complicated kinds of measures, we could also come up with ways of fitting them, but we might not be able to get an optimal solution. We could at least pose whatever objective function we wanted and try to minimize relative to that objective function. It's a more general kind of optimization problem. So any questions about that? All right, so that's just showing some of the ways we can get best fit polynomials by different definitions. And of course, there are times we don't want polynomials. So there are alternatives to this, some of which there's a lot of theory developed for them, some of which you would kind of have to come up with something ad hoc. One example, it's not used as commonly, but I'll just mention, is called rational function approximation, or rational function interpolation. So a rational function is simply a ratio of two polynomials. So we could say that there's some R of x that's approximating our data, where R of x is a ratio P of x over Q of x, where P and Q are both polynomials. So P0 plus P1x plus P2x squared, etc., through Pk x to the k. And then Q would be similarly Q0 plus Q1x plus Q2x squared up through Qk x to the k. That would be a rational function approximation of degree k. And these can have some advantages over polynomial fits. Can anyone think of what a rational function approximation might be good for? Well, there's some things a rational function can do that you can't do with a polynomial. So, for example, a rational function can go to a finite limit. So it can kind of converge to some constant. Polynomial can't do that. It's going to go to plus or minus infinity in the limit. And a rational function can also have, can blow up within the region that we're interested in. So you can have an asymptote, and that also is something you can't do with a polynomial. So basically, there's some kinds of behaviors these can capture that won't be captured well by a polynomial. And it turns out that there are formulas analogous to Nepals' method for rational function approximation. So I'll just write one here. I'm not going to go through the theory of it at all. We can define something analogous to Nepals' method to say that we can create a rational function I plus m by taking rational function I plus 1, I plus m, and adding to that the following term, r I plus 1, I plus m minus r I plus m minus 1 divided by x minus xi over x minus x I plus m times 1 minus r I plus 1 I plus m minus r I plus m minus 1 over r I plus 1 I plus m minus r I plus 1 I plus m minus 1 minus 1. So a much more complicated formula. I'm not going to try to prove why that formula is correct, but it basically lets us do something analogous to the Nepals method to generate rational function approximations for a set of points. There are some other very widely used methods that are worth knowing about that I'm not going to talk about in this class. So one that I've always debated whether I should add it here, but decided not to because most people see it elsewhere, is Fourier interpolation. So if you know about Fourier transforms, discrete Fourier transforms, it's a way of representing a set of data points as a sum of a family of sinusoids. That's another kind of approximation that's often very useful. And there's a related thing you see a lot in kind of signal processing contexts called a wavelet transform. So wavelet transforms can also be used to do a kind of interpolation that's similar to these. But these are things you can learn more about in other places. There's some references in the text if you really want to know about these. I'm kind of curious, just by a show of hands, how many of you have studied Fourier series in one class or another? I guess that's not covered as much as it used to be. I think when I was a student, I must have had at least 5 different classes that went through that. But maybe I should start introducing it in the future. But just be aware that's another important alternative to these methods. Right, but basically those are all ways we can get for taking a set of points and finding an interpolant that does a decent job of fitting all of the points. In some contexts, though, that's not quite what we want. So there's often a kind of a tension when we have a large set of points between trying to get good local approximations and trying to get good global approximations. So if we've got a very long series of points, if you try to fit a low-degree polynomial to them, the odds are you're going to get something that fits very poorly pretty much everywhere in the curve you're looking at. But if you try to fit high-degree polynomials, you may get the kind of crazy behavior I was talking about before, where it's just sort of swinging all over the place. So in some sense, what you want is something you can't quite do with polynomials, or at least you can't quite do with one polynomial, and that is get a nice smooth fit in each local region of the curve, but also get a good global fit that doesn't kind of drift away from the curve as you look at very large numbers of points. And what I'm kind of getting at here is a class of methods where we try to do our interpolation by, instead of getting one global interpolant, try to get local interpolants within each region of the curve. So you've probably all seen the simplest way of doing that, and that would be to do a piecewise linear interpolation. So we just take each pair of consecutive points, draw a line between them, and then we say that's our interpolant. Anywhere we want to know about a point between our measured values, we just use the line between the 2 nearest points. That kind of interpolation can be fine for some purposes, but it has problems for some of the reasons we would want to do interpolation. So let's say, for example, we were looking at the example I mentioned way back at the beginning of the class. We've got a differential equation model of maybe a regulatory network in a cell, and we're trying to drive it with some external signal. And we do a piecewise linear interpolation like this to get a smooth curve from our experimentally measured points on the driving signal. What problem is that going to create? Well, that kind of thing is generally going to be an issue for numerical integration, actually for lots of numerical methods that we use, because these methods depend very heavily on taking derivatives. So if you have a piecewise linear curve, the derivatives are discontinuous. So if you're doing anything that depends on, let's say the error analysis depends on the second derivative, which would be true of, let's say, a forward Euler method, the second derivative is infinite at each of these points, so your methods are going to perform very poorly. So often for these kinds of applications, and even just for general use, if we want a better looking curve, a smoother looking curve, there's a class of techniques that's actually primarily used in computer graphics and animation that tends to be really useful for these kinds of problems, and those are known as splines. And a spline is basically a way of getting better approximations to a set of points like this that give you a kind of a less choppy fit, that kind of have local interpolants like this, but put them together more smoothly so you don't get these kinds of discontinuities. And the idea behind this we can illustrate by starting with a way of thinking about the piecewise linear problem and then seeing how to generalize that to get a better set of approximations. So let's say we've got 4 data points, and I'll call these data points x1, y1, x2, y2, x3y3, and x4y4. What we're trying to assert in the piecewise linear case is that we want three functions, so a linear function from here to here, one from here to here, and one from here to here, that will get the endpoints of these intervals right. And we can say that we'll have one function, let's call it S12, which will be some coefficient C1 comma 0 plus C11 times x. And this will be one where we're trying to fit the C10 and the C11 so that they match these 2 points. And we'll have an S23, which will take the form C20 plus C21x, which will match these 2 points, and an S34, which will be C30 plus C31x, which will assume matches points x3y3 and x4y4. We already saw a couple of ways we could find these interpolants, but I want to write them in a slightly different way, and in particular to write them as a solution to a linear system. So what I'm claiming about these points is that they basically satisfy a few different constraints. We're claiming that S12 of x1 is equal to y1, and that S12 of x2 is equal to y2. That's what S12 has to satisfy. We're claiming that S23 of x2 equals y2, and S23 of x3 equals y3, and we're claiming that S34 of x3 equals y3, and S34 of x4 equals y4. Those are the things we're asserting these should satisfy to be a correct piecewise linear approximation. And if we just plug in these equations here, we end up with a set of linear equations that are the assertions we're trying to make about these interpolants. So in particular, we can phrase this as follows. We can say that we've got a matrix. We've got our set of coefficients here. We've got 6 coefficients we're trying to learn. C10, C11, C20, C21, C30, C31. And then our constraints can be put into the following form. We can say that this first constraint is equivalent to asserting that 1 times C10 plus x times C11 is equal to y1. So we can phrase that as 1 x1, 0, 0, 0, 0 equals y1. And the second equation here is equivalent to asserting that C10 plus C11 x2 is equal to y2, which we can say is equivalent to doing 1 x2, and I just won't bother writing zeros, is equal to y2. And we can similarly say that the next equation is equivalent to putting 1 x2 times C20, C21 is equal to y2, 1 x3, C20, C21 is equal to y3, and 1 x3, C30, C31 is equal to y3, and 1 x4 times C30, C31 is equal to y4. So in other words, what we end up with here, just putting zeros everywhere else, is a linear system whose solution will tell us the constraints that give us all of our piecewise linear interpolants. So does that make sense to everyone? Right, so the spline idea says that we can generalize that by taking higher order terms but throwing in extra constraints that will basically force them to give a smoother fit. So if we want to get rid of the discontinuities in the derivatives, for example, we can say that instead of getting piecewise linear fits, let's assert that we're trying to find interpolants S12, S23, and S3, or maybe S34, like before. But we'll now assume that these are quadratic, so we've got a little more freedom to play with. So these will be C10, C11x plus C12x squared, C20 plus C21x plus C2 c2, 2, x squared, and c3, 0, plus c3, 1x, plus c3, 2, x squared. Those will be our interpolants. And we'll insist that, just as before, the first interpolant matches the first 2 points, the second one matches the next 2 points, third one matches the next 2 points. But we'll also insist that where they link together smoothly. And what I mean by linking together smoothly is that we'll insist that ds1 dx at the point that links these together, so x2 will be the same as ds23 dx at the same point. So at the point where those two join together, we'll insist that they not only both have to match the value of that point as given by the constraints over there, they also have to match the derivatives at that point. They have to have the same derivative. Does that make sense to everyone? All right, so we can update our assertions that these match the values we want. So for any of those particular equations, let's say S12 of x1 equals y1, that still is a linear constraint. That's equivalent to saying c10 plus c11 x1 plus c12 x1 squared equals y1. It needs to be linear in the c's, not the x's, so this is still a linear constraint. But this is actually also a linear constraint in the coefficients. So in particular, if we take the derivative of S12 with respect to x, what is that? Well, it's the derivative of this thing with respect to x. So ds12 dx is going to be equal to this derivative of a constant is 0, derivative of a coefficient times x is the coefficient, so c11, and then we've got a c12x squared, the derivative is 2 c12x. And we would have the analogous thing for S23, so the assertion that ds12 dx at x2 is the same as ds23 dx at x2 is equivalent to saying c11 plus 2 c12 x2 is equal to c21 plus 2 c22 x2. And with a little rearrangement, that's the same thing as saying c11 plus 2 c12 x2 minus c21 minus 2 c22 x2 is equal to 0. So that is what we're asserting, and this also is linear in the coefficients we're trying to learn. Does that make sense to everyone? Okay, so what we can do then is take all these linear constraints and try to generalize this matrix approach to learning our spline. And what's going to look like is something like the following. So we'll have a matrix. We'll have our set of coefficients. We're now assuming that we're learning 3 quadratic equations. So we'll have 9 coefficients, C10, C11, C12, C20, C21, C22, C30, C31, C32. And then we can go through and try to write down all of the constraints we have. So we've got some constraints that are equivalent to assertions like this one, that we match the points at the endpoints of the interval. So, for example, we'll still need a constraint that says the first polynomial matches the first point, and that would be equivalent to saying 1 times c10 plus x1 times c11 plus x1 squared times c12 is equal to y1. And we would likewise want to assert that that matches at point x2, which would mean that 1 x2, x2 squared times these first 3 coefficients is y2. And then we'll come to the constraint where we want to assert that at point x2, y2, the first interpolant has the same derivative as the second interpolant. And we saw here how to put that as a linear constraint. And what it's going to look like is the following. We're going to have a 0, 1, 2x 2x2, and then equivalent to saying c11 plus 2c12x2 minus c21 minus 2c22x2 is equal to 0, which is the thing that asserts that they have the same derivative. Does that make sense to everyone? Okay, so we could keep going here and put in other constraints. We could say that the second interpolant has to, let's see, it has to have a value that is equal to the value of the second point, 1x2 x2 squared equal to, I have to put a 0 here, equal to y2, 1x3 x3 squared is equal to y3, that's asserting the second interpolant matches the third point. And then we could throw in another derivative constraint that says that at the third point, the second and third interpolants have the same value, or the same derivative. And that would look like 0, 1, 2x3, 0, minus 1, minus 2x3 equal to 0. And then we would just need to throw in two more of these constraints saying that the third interpolant matches the third and fourth points. That's going to look like, let's see, 1 x3, x3 squared equal to y3, 1 x4, x4 squared equal to y4. And what we've got then is a linear system that's asserting that we've got values of the coefficients where each interpolant matches the two endpoints of its region, and the pairs of interpolants have the same derivative at all the points where they touch. So that would give us a much smoother fit to our data set. There's one small problem here. Can anyone see what it is? If we actually try to solve this system, something's going to go wrong. Well, the problem is we've got 8 equations but 9 unknowns. So this is an underdetermined system. So one thing we could do here is to throw in an objective function. We could say that we want the solution that minimizes, let's say, the sum of absolute values of the coefficients. That would give us a linear program. We could say that we want to get a solution that minimizes the sum of squares of absolute values of the coefficients. That would give us a quadratic program. But often what we would do is something that's somewhat simpler and lets us still solve this as a simple linear system solving solution. And that is to just throw in one extra constraint on the derivatives of the problem. So a typical thing to do would be to say, if we have no other reason to believe anything in particular about what the coefficients should be, let's just assert that the derivative of the first interpolant at the first point is 0. So we could throw that in by saying that we would have this extra term here, 0, 1, 2x1 equals 0. And then what we would have is a full rank system that's going to satisfy the constraints we want of our splines matching the endpoints and matching derivatives everywhere they touch. Right, so that's basically the idea behind spline interpolation. So any questions about this? Okay, so I will say just one thing to be aware of here. Usually what we would do is actually go to a slightly higher order version of this. So most commonly what people do is cubic splines rather than quadratic splines. And with a cubic spline, you would say that every spline matches the two endpoints of its region, and where they touch, they have the same first derivative and the same second derivative. So for graphics kinds of applications, that just looks a lot better to the human eye, but also gives you one more derivative that matches. So if you're using them in a numerical integration or whatever, it will avoid these kinds of discontinuity problems up to a higher order of accuracy. All right, so any questions about any of that? All right, so this technique can be generalized like the other ones we talked about. There's nothing that says these have to be polynomials. You could do the same thing with any function as long as the function is linear in the coefficients you're trying to learn. And even if it's not linear in the coefficients, you maybe can't solve it as a linear system, but we could still pose the problem of finding the coefficients that fit for some arbitrary family of curves interpolating between our points, but usually polynomials kind of do the job. Right, so that basically gets us through how we would typically do interpolation if we were looking at, let's say, a function of a single dependent and a single independent variable. I'll just briefly mention the problem of multi-dimensional interpolation. So more or less the same ideas, to some degree generalized, if we were trying to look at a function of multiple independent variables. So let's say, for example, we're trying to do an interpolant on a two-dimensional image. It may be that we've got some grid, and we're assuming that we know values of the pixels at grid points, to that effect, and we want to know what the value would be at some point in between those grid points. We can come up with generalizations of some of the methods we've already seen. So splines are a lot messier because then you're no longer matching points, you're matching edges. That's a more complicated thing. But some of the simpler methods generalize pretty easily. So a common thing to do would be what's called bilinear interpolation. And the idea behind bilinear interpolation is that we would try to predict the value of that point by a weighted average of points at all four corners of the square it's in, or if you're doing this in 3 dimensions, you interpolate based on a cube that contains it or something like that. But basically the idea behind this would be, we would say, if we know some set of points xi, yj, xi plus 1, yj, xi plus 1, yj plus 1, and xi, yj plus 1, we want to know the value of some xy in between, we basically just try to figure out how close is xy to each of these endpoints. We could say that there's some t equals x minus xi over xi plus 1 minus xi, u equals y minus yi over yi plus 1 minus yi, and then basically come up with an interpolant where we do a weighted average of these 4 points based on these t and u values. So we can say that we'll assert that the value of our function at point xi is going to be proportional to 1 minus t, 1 minus u, times the value of the point in, let's see, that would be in this corner, f of xi yj, plus t, 1 minus u, f of xi plus 1 yj, plus 1 minus tu, f of xi yj plus 1, plus tu, f of xi plus 1 yj plus 1. So that basically would just be a generalization of linear interpolation to multiple dimensions. And it's not too hard to think of more complicated kinds of interpolations. So fitting a multi-dimensional polynomial based on multiple points around the region. So there's a kind of general technique called response surface fitting, where basically you try to fit a quadratic to points in the area around this, or a cubic multi-dimensional function, whatever family of functions you want. And basically all the techniques we've seen will generalize to, most of them will generalize to that case. I'll just mention one other kind of method that's often useful for these problems. This is one, it's not in the text, but I think it's a good one to know about, called Gaussian interpolation. It's a very easy one to implement if you want to do multi-dimensional interpolation. The idea behind this is, if we've got a set of multi-dimensional points, let's say x, y, z, f, then what we do is, if we've got a set of these x1, y1, z1, f1 through x1, y, or xn, yn, zn, fn, and we want to know the value at a new point, x, y, z, and we're trying to figure out what f is based on x, y, z. The idea is that you just do a weighted average over all of the points, treating each point as if its weight were decaying like a Gaussian function as we move away from the point. So in other words, f of x, y, z at a point not in our point set would be sum over I of fi e to the minus x minus xi squared plus y minus yi squared plus z minus zi squared over 2 sigma squared, and then divide that by the sum of these weights, e to the minus x minus xi squared plus y minus yi squared, z minus ci squared over 2 sigma squared. And what this is basically saying is that we're taking a weighted average where the closer we are to a particular point, the more weight we're throwing on that point. And this is a kind of method you can tune by shifting the sigma value. If you make sigma very big, these decay slowly, so you get something that's averaging many points around it. If you make sigma a very small value, then it puts a lot of weight on the close points, so it kind of tunes how rough or smooth you want your interpolant to be. So that tends to be a good, very easy method if you need to do multidimensional interpolation. All right, so any questions about any of that? All right, so I will say just briefly that we can do much more general kinds of fitting than these standard methods I'm telling you about, and we already pretty much know how to do that. So I just want to briefly go through an example of how that might work. So let's say we were trying to do interpolation on a set of points, and we believe that the points are actually described by an exponential function. So maybe we have a set of points, x, y, and we believe that y of x is of the form a plus b e to the minus cx for some unknown a, b, and c. Can anyone tell me how we could find the best fit a, b, and c? Like, let's say find the least squares fit for a, b, and c. Well, yeah.
Can we do log transformation?
Well, you could. In this case, if we were doing a likelihood, like multiplicative function, that would tend to be a good way to start. In this case, that's probably not really necessary, and we can start by just saying what it is we're trying to optimize. We're trying to minimize some phi of a, b, c, which if we're doing a least squares fit, we're defining to be the sum over our data points I of a plus b e to the minus c xi minus yi squared. This is just some function of a, b, and c. We're trying to minimize that function, so we could come up with an arbitrary numerical optimizer. We could do, let's say, a steepest descent optimizer. To do that, we would want to find d phi dA, d phi dB, and d phi dC. All of those would be not too hard to find, so this is just a linear sum of a relatively simple term here. So we would end up d phi dA is the sum of 2 times a plus b e to the minus c xi minus yi. d phi dB is sum over I of 2 e to the minus c xi a plus b e to the minus c xi minus yi. And d phi dc is sum over I negative 2xi a plus b e to the minus c xi minus yi. So in this case, we can get an analytical expression for the gradient of our function, and if we've got the gradient, we can create a steepest descent solver. We could get second derivatives, get a Hessian matrix, come up with a Newton-Raphson solver. Basically, it's just a numerical optimization problem, and we know how to do those. Does that make sense to everyone? What if, instead of this being a plus b e to the minus cx, we expressed y of x as some system of differential equations, or just some other complicated to compute thing where we couldn't get analytical derivatives? What would we do? If we couldn't analytically compute the derivatives, we could still compute them numerically. So we could run our solution, as long as we're able to evaluate values of the objective function fit, then we can use numerical derivatives. We tried perturbing a little bit, then we could get phi of a plus delta a minus phi of a over delta a. That's an approximation to d phi dA. We could do the same thing with b and c, and we could still come up with a steepest descent optimizer. Does that make sense to everyone? Okay, so that basically is just supposed to show you that we already have a lot of tools available to us to do this kind of solving. There's one last thing I wanted to mention. I think we won't get through all of the material in the text, but I just do want to talk about it in the last few minutes of the class, and that is the problem of extrapolation. So extrapolation is sort of like interpolation, but we're often trying to find the limit of some infinite process, or the limit as, let's say we go to an infinite number of data points in some search, or in some other way, a limit that would be hard to compute directly. And I'll talk about one method briefly, known as Richardson extrapolation. And then there's another we won't have time to get to, called the Aitken delta squared method. It's in the textbook that works in some other kinds of cases. But Richardson extrapolation is a technique that tends to be good when we have a way of evaluating some function g, which is a function of a parameter h, and what we want to know is g of 0. And this is something that might seem like an odd question to ask, but it actually comes up quite a lot in numerical methods kinds of contexts, because many of the things we're looking at are problems where the closer h gets to 0, the harder it gets to compute what we're trying to find. So for example, numerical integration, where h is the step size. So if we're trying to do numerical integration and h is delta t, we can find the numerical integral for a large delta t because we're not taking many steps. But what we really want to know is the limit as delta t goes to 0 and the accuracy becomes infinite. That's a case where Richardson extrapolation would be useful. And it particularly comes up in contexts where g of h has the particular form c0 plus c1h plus c2h squared, etc., as an infinite series. And that also may sound somewhat specialized, but it comes up quite a lot in practice, because again, if we think of h as a step size and delta t, this is the form of a Taylor series in the perturbation. So lots of functions we're trying to approximate have an error analysis that looks like this. So we would get g of delta t is c0 plus c1 delta t plus c2 delta t squared, and so forth. And the idea behind Richardson extrapolation is really simple. So simple you might think it can't possibly work, but it actually often does work very well in practice. And the idea is we take an approximation with one value of h, like you run your integrator with one value of delta t, and then you do the same thing with a different value. So cut delta t in half, run your integrator again, and you get c0 plus c1 h over 2 plus c2 h over 2 squared, etc. And then just take a linear combination of these. So in particular, what we're going to do is take 2 times this minus this. That's going to give us 2c0 minus c0, which is c0, 2c1h over 2 minus c1h, which is 0. These cancel out. And then a quadratic term. So what we're going to end up with in the quadratic position is minus c2 h squared over 2, and then we'll have a cubic position, c3 7h squared over 8, and then lower order or higher order terms. So we've taken a linear combination of 2 first-order approximations, and we've derived a second-order approximation. And you can do that again. So if we call this g hat of h, then we can try g hat of h over 2. You can plug in that. That'll be c0 plus 0 minus c2 h over 2 squared over 2 minus, let's see, that would be c3, 7, h over 2 squared over 8, and so forth. And we can do a linear combination of these two things, and we would end up with 4/3 g hat of h over 2 minus 1/3 g hat of h. Ends up giving us c0 plus 0 plus 0 plus an order h cubed term, and so forth. So this gives you a very simple way of taking a low-order accuracy approximation, trying it at a few different values, and combining them to get higher-order accuracy approximations. So for numerical integrals like this, where you have an error expansion that can be written as a Taylor series. So it's one of these things that it almost seems like magic that it could possibly work, but it actually often works very well and gives you a way of getting very rapid acceleration of these kinds of techniques, much better accuracy than is seemingly possible. It doesn't always work, and the reason could be that in some of these, the high-order terms start blowing up, and then all of the theory kind of falls apart. So you're not guaranteed it would work, but it does work very well quite often in practice. All right, so any questions about that? Right, so I think we're out of time here, so I'll just say, read the text if you want to know about the Aitken's delta squared method, and I'll just hand out the next homework assignment. If you haven't handed in your assignments yet, please do so.
Oh, yes.